Hi everyone. Hi everyone. So we're going to begin our second talk now. So this is Sihun giving us a talk on conformal field theory in 2D, Mobius geometry, and the highest weight representation of Virasoro algebra. But yeah, give him a warm welcome.
Right, yeah. Thank you. So now I'm going to talk about conformal field theory, which is a subset of quantum field theory. But before that, I'm going to introduce you to some notation I'm going to use throughout the talk today. It's a way of writing tensors. And so whenever I do something like this is not x to the power of m, but it's the mth component of the vector x. And that's what we call a contravariant vector tensor. And I can also do index down, but that means covariant tensor. It's not hugely important, the difference, for the purpose of this talk. It's just the way that it transforms depends on whether the index is up or down. But I'll explain later how do you do the transformation and everything. And whenever you see index up and I don't know, index down, and if you have the repeated indices, it means the index is summed over in some, I don't know, n to, let's say, d-dimensional vector. That's what it means. I'm not going to do sum. When it's repeated, you can just think of it as a repeat. So first things first. So we'll mostly talk about flat space-time, which is you can think of it as a Euclidean space. We call this Minkowski space in physics, and what that means is when you have the notion of distance within the space, we measure that the infinitesimal distance element, this is a power, as this is a metric tensor that depends on the coordinate, d mu, d nu. That's how you measure the distance within the generalized coordinate system. And in Minkowski space, if you have, let's say, p time dimension plus q space dimension, the metric tensor is equal to 0 everywhere, -1, -1, 1, 1, and p of this, q of this. And everything is 0 except for the diagonal entries. And that's how we do the basically Pythagoras theorem for the generalized space, flat space. Yeah. So in this space, when you have a vector v and w dot product, it means g mu nu. That's how you do the dot product. And then now we can finally talk about what conformal transformation is. So if you have a diffeomorphism, it just means coordinate transformation. X to X, something like that. Oh, I can think. Time actually. Then the metric tensor transforms as which is equal to some scalar function times the original metric. So we say the metric tensor is invariant up to a scalar vector under this transformation. That is what we mean by conformal transformation. And then the conformal group is the subgroup of the group of all the coordinate transformation that leaves the metric in this form, basically. And the first thing to notice is that when you have an angle between two vectors in the original coordinates, and the angle is defined as this. This is it's the same thing because there's a metric tensor here, here, and here. You can multiply by sigma. It's the same thing. So conformal transformation, it can also mean angle preserving transformations. Yeah, that's that. And then I'll give you a brief introduction of what Lie theory is. So I said there's a notion of manifold, which is a generalization of, oh yeah.
Sorry, so I guess in the interest of all the mathematicians here,
Yeah.
what is really x mu and what is there about it?
What is x mu?
What is this?
Okay, yeah. We have this space here, right? X is an element of this space. And this is how you specify where you are in the space. So this is the coordinate. And sorry. So x mu is the component, mu's component of x vector. And here I'm saying mu's component of G depends on the vector x.
So this is a map from the mu coordinate of an element in space-time. What is this? What are the domains and codomains of this map? I'm confused.
Okay, so you want me to define what G is?
No, what is this? You say G, this is conformal map, is a map from x mu to x prime mu. What is this?
Oh, this one. It's basically a diffeomorphism. It's an isomorphism between two manifolds. So
But you say x is one position in space-time.
yeah,
So how is x mu a manifold? It's just the mu's coordinate. Am I missing something?
so for all mu, this Mills component transforms maps to the new coordinate for all mu. We can just also say like this. Yeah. Any questions?
Is it a map from a space to itself, or is it another space?
It's a map from a space to itself.
Okay.
Automorphism. No questions? Yeah. So I'll be a bit wishy-washy about all the proofs and stuff. But you can see, oh yeah, I forgot to mention. There's a note I'm using at the top in the GitHub if you want to see. And below that is the lecture note by Ginsparg. It has some more detailed proofs and everything, if you want to see. Yeah, back to Lie theory. So I just talked about manifolds a bit. So the definition of manifold is a space that is locally flat enough to be considered as a Euclidean space, which allows you to do the calculus locally. So it's a locally differentiable space. So Euclidean space is flat in this sense, but there could be something like this. But if you zoom in, this becomes Euclidean. That's what I mean by differentiable manifolds. So naturally, one can define the tangent space at a point on a manifold, which is globally differentiable. And if you have a curve on the, like a path in a manifold from, let's call this point x. X mu really means a vector. It's the same thing. But yeah, let's call this point x mu. And if I want to move along the curve, I can find a vector in the tangent space that is parallel to the line of the curve. And so, okay, let's define tangent space at x mu of the manifold. There exists a vector m, and from this point to go to this point, we do a transformation, coordinate transformation with the infinitesimally small number with that element in the tangent space, which yes. So that's what manifold is. And the definition of Lie group is a group with a manifold equipped with a binary operation. So instead of finite set, we have manifolds. That's what a Lie group is. And the Lie algebra is defined as a vector space is a vector space G over some field. With a binary operation, we call it Lie bracket, satisfying three axioms, which are bilinearity, and alternating property, for all x in the vector space. And lastly, Jacobi identity Z x plus Z x y equals to 0. This is just generalization of Leibniz formula. When you differentiate it, it'll be clear why you use it when you make a connection with the Lie group. So the reason why this is called Lie algebra is because when you have a Lie group, it gives rise to a corresponding Lie algebra as a tangent space of the manifold of the Lie group about the identity element of the Lie group. And you can, commutator satisfies this relation. So you can say that the Lie algebra is a vector space. So let's say this is your Lie group, and you have identity here. This is manifold. The tangent space is the Lie algebra, and from here, if you wanna get to this point, from that point, sorry, like so. That is equivalent to, that's the identity point, plus the tangent vector, some small number delta t times the tangent vector in the Lie algebra. Yeah. So when you have a element of the Lie group here, this is an element of the Lie group. X transforms to, you can operate this on X. And that means this is a new transformed X. That means the difference in X, I'm going to just do this minus that, which is delta t x x. And you're going to do what physicists do when we have infinitesimal differentials. It's d by dxt equals x times x. And voila, that's, if you solve for x at t is equal to e to tx times x at t equals 0. It's a differential equation, kind of. So when you have an element of the Lie algebra, you can generate an element in the Lie group by exponentiating, like so. And why this thing matters is because there's a thing called Baker-Campbell-Hausdorff formula, where it says given x and y, in the Lie algebra, if you want to find another member of the Lie algebra set, the formula is given by x plus y plus half. It's not really important what it exactly is, but what's important is it's a series of the Lie brackets, nested Lie brackets, plus blah blah blah, plus blah blah. So Lie bracket is important because it determines the structure of the Lie algebra, Lie group, using this formula. And we can easily see if the Lie bracket is 0 for all elements of the Lie algebra, it's just x plus y, which is familiar notation for exponentiating and everything. Okay. So now we start talking about conformal field theory, finally, in higher than 2 dimensions. So when we have an infinitesimal generators of conformal group, let's say you have a diffeomorphism that maps to x of mu, x of mu plus some function of x, and we just say this is small, infinitesimally small, and from this we can derive, using this relation, the full proof is in my note up there in the GitHub, but I'll just tell you what the form this should take in order to make the metric to transform in such a way. It is D is the dimension the number of dimension of our theory. And I forgot to tell you, if we are in the Minkowski space, we just denote the metric tensor as eta. So that means it's diagonal, like so. And partial mu, it means partial dx. Just a notation. And we say this is covariant derivative because we are in a flat space. But it usually isn't a covariant derivative, but we can take it as a covariant. And if you multiply eta mu partial mu on both sides, you get eta mu dial inversion plus t minus 2 t mu dot epsilon the inversion is equal to so this is the differential equation of order 3, and that means from this we can see that epsilon, which is a function of x, is at most quadratic in x because it has to annihilate all the x to make it 0. This equation is important. I'll just call it equation 1. So we'll do a case study. For the values of, for the possible values of the epsilon can take. When epsilon is constant, A is a constant, it doesn't depend on x, then the generator, the member of the Lie algebra, is in this form. So x transforms as such. So I'm exponentiating the differential operator. You can do the Taylor expansion of it and operate it on x. Then you get x plus some vector, constant vector. That means this when epsilon is constant, your transformation, your conformal transformation, is a translation in x. You're just translating the whole coordinate by x. And if epsilon is linear in x, in this form, nu x nu, this omega is a matrix. And it's constant, it doesn't depend on x. And if you plug this in to that equation 1, you can see that omega mu nu is 0. So when you swap the indices, it becomes 0. It means the omega is antisymmetric or skew symmetric. So omega transpose. It's the negative of the transpose. Then the transformed vector kx is omega w x so that becomes well, the generator is first of all omega mu x mu t and alpha. It becomes some matrix. Let's call it lambda x, where lambda is in special orthogonal group of p and q dimension. It just means a rotation in p plus q dimension. Yeah, so it's a rotation. This generates a rotation. And if you have a linear epsilon like so, then your generator is this, and your transformed, when you exponentiate it, transformed vector becomes something like that. So you can define, I don't know, lambda as 1 plus L. So scaling is what you get from that epsilon. Yep, scaling. And lastly, when epsilon is quadratic in X, this form might look a bit random. 2 is not indices, is a squared. But this is the solution to the quadratic solution to this equation, the Killing vector equation. Bx mu p x. And what you get is from that x mu divided by x squared. I'm just going to show you this because it's easier to see what it is from this form. Plus b mu. So this is an inversion plus translation. And it's an inversion, let's see. About the plane, the surface 1 plus b 2b dot x plus b squared equals 1. About this surface, this is inversion. And that we call this inversion special conformal transformation. but it's not really important like, exactly which form it takes. What's important is these four transformations, translation, rotation, we call this scaling dilation, and then special conformal transformation. There are the only four types of the transformations that is possible under the conformal transformation. The proof is, the theorem is called Liouville's theorem, and you can have a look at the Wikipedia for the proof. Yeah. So that was dimension larger than 2. But it gets interesting when the dimension's 2. Because in this space, R2, the metric is just chronicle delta, which is the identity, 2x2 identity matrix. And if you plug that in, this equation again, you get this relation where the indices down means this is the first component, the second component, first component, second component. Yep.
Sorry, you previously defined this, what do you call it, as a metric tensor?
Yeah, metric tensor.
For Minkowski space-time.
Yeah.
And you put the negative ones for the space dimension,
Yeah.
ones for the time dimension.
Yeah.
So are we supposed to think of this as 2 time dimensions? What does that mean?
It's either 2 time dimension or 2 space dimension.
Okay.
Yeah, yeah. And then we can do some rotation to go to 1 + 1 dimension. But now we are thinking of it as a 2 space or time dimension. Good question, yeah. So it becomes this equation. And for those who know a bit about complex analysis, you should be familiar that this is Cauchy-Riemann condition for the analysis of the function. So if we complexify the coordinates, x1 is the first component of x plus I, x2, z bar, like so. We can see that the group of all conformal transformation is any entirely analytic function which satisfies that equation, so it has to be less than second order. And we can see this. We can say this is in C. But if we compactify it into a Riemann sphere, so I say it's union point at infinity. So this is 2D sphere. Yeah, 2D sphere. the conformal group in the Riemann sphere is equal to f of z, which is in the form z plus b cz plus d, such that a, b, c, d are in the complex, and the circle determinant at a, d, c, b is non-zero to make it invertible, because it's a group. We'll see why this is true later. And yes. So to analyze this further, we will consider the Lorentz series of the epsilon. So of the infinitesimal. So the basis, let's say the basis of the infinitesimal transformation is this is a subscript or a component. Just labeling what it is. Is equal to, let's say, z minus small number epsilon z to the, this is, I'm just choosing this number because it turns out to be convenient later. So that means if we call the infinitesimal generator ln, for this transformation is minus z n plus 1 z. And from this, we can do the commutation relations. This is also defined for the z bar coordinate, which we kind of treated as an independent coordinate. And it's a commutator is defined like so. If you do this with all possible combinations of this, we get m minus n, m plus n. And same thing for the bar, like that. And when you have two different, then you get 0. And that's the closed form of the Lie algebra of the conformal group we have there. And from this you can see yep. Oh yeah, sure. So that is the local algebra And we can see that this is infinite dimensional. So you have much more interesting, you can do things more freely because you have less restrictions on your theory. And from that, basically, you can generate two independent copies of the algebra. One formed by this, and another one, let's call it A, another one formed by this bar. Let's call it A bar. And because they commute with each other, you can do direct sum of the algebra to get what's called Witt algebra. And there are much more to do in terms of expectation values of different particles in quantum field theory. You can make several constraints on which thing depends on what and so on. But that all just comes from the symmetry we had at the beginning. Oops, sorry. Which is from this we can derive everything. So yeah, that's the beauty of conformal field theory. Thank you.
Okay, thank you, Stephen, for the talk. So yeah, we will have lunch quite shortly, whenever we get there, basically. And then after lunch, we have in-building activities.